Okay, so I'll recall last time we proved this lemma. So suppose I have a geodesic triangle ABC. Inside my space P and R, and I say I denote the length like this. So then I have this inequality that C square is bigger than equal to A square plus B square minus twice AB cosine the angle at C. And second part of this was that equality holds. Suppose that C is identity. This point C is identity. Then equality holds if and only if this triangle ABC is contained in the orbit of an abelian subgroup, abelian subalgebra of the symmetric matrices. So I'll just make a remark on this, and then I'll continue. The remark is that towards the end of the proof, so remark on the proof, the second one. So the argument that I sketched last time actually proves a little more than this. So if you assume that C is at the identity, so suppose A is exponential x and B is exponential y, then I claim that so you can easily prove this, that exponential tx, okay, and exponential ty. Suppose this subalgebra is yeah. So yeah. So I don't mean 1 second. Yes, no, this is not the statement that I wrote down last time. So contained in the orbit of some abelian subgroup inside this. Subgroup inside GLN R intersected with PNR. Okay, so now let us call this H. Let us say this subgroup is H. So say the subgroup is H. So these are inside this for all T. That was the claim. Okay, so yeah. So more precisely, I mean this is in the orbit of. So I should say that maybe, yeah. So these are in the orbit of this subgroup H. So that will imply that these two are inside H for all T. Okay, and then so this will imply that so this I left this as an exercise for you to check this. And so therefore you see that how do I then complete the proof? So the easiest way to see is that therefore I have, since H is abelian, then exponential Tx times exponential Sy is equal to exponential Sy times exponential Tx. Okay, and then apply the differential operator, partial differential operator. So let's say first apply del del t and then del del s, and evaluate at 0, 0. So this will imply that we apply this to this identity, and then you will get that xy equal to yx. So once you do that, then you can apply this the first part, that when they commute, if xy commute, then, and so this geodesic e to the this one was t going to e to the exponential tx, and this was t going to exponential ty, and if x commute, then this is an equality. So you can use that, the first part of this, and then that will complete this proof. Does it make sense? Is it okay? So last time we proved that, suppose I have one geodesic t going to exponential tx and another geodesic t going to exponential ty. So if xy commute, then this equality will hold. Right? That was the first part of this second portion of this lemma. We are trying to prove the converse. Right? And so this one, this will complete the proof of 2. So I just want to make a remark about a possible confusion. So, suppose I have an abelian subalgebra. So let's P inside S in R be an abelian subalgebra. Okay. So then exponential of that, this is a exponential of this thing, let's say h. This is an abelian subgroup. Subgroup contained inside GL in R intersected P in R. Okay. So this is sitting as a subset of P in R. Okay. And also now you can consider the H orbit of identity inside P in R. So those two are same. So check that. Easy to check. H, it looks like trivial, right, like this, but here the multiplication was different, so it was G times G transpose, but H is self-adjoint here. So this will imply this. The image of H under the exponential map is same thing as the H orbit of identity. So this is the remark that I wanted to make. Is it okay? So now, so we'll continue with something new. So this is one, and so now note that, so if this is the case, so yeah, maybe I should write here. So, so note that in this case, the exponential map from V to exponential V, so this one, this is an isometric embedding. So V is inside some Euclidean space, so it has a metric. So V is the inside the tangent space of identity, so it has a metric. It's an Euclidean space, and this one, because of that equality, will have that this is an isometric embedding. The exponential V therefore is isometric to some Euclidean plane. This is true for any abelian subalgebra. So here is a definition. So a flat in P and R, so more generally any symmetric space of non-compact type. So a flat inside that is an isometrically embedded copy of Euclidean space. Copy of an Euclidean space. N-dimensional Euclidean space. Okay. And So a maximal flat is a flat of maximum possible dimension. Maximal flat is a flat of maximum possible dimension. Okay? And this maximum dimension rank of this space. Rank is defined to be the dimension of a maximal flat. So of course, okay. So yeah, so I have to say that this will be well defined only if all the maximal flats have the same dimension and so on. But this will follow easily in our case. So here is a proposition. Every flat is contained inside a maximal flat. And then G ln R in our case. So all these kind of statements, they will be true for general symmetric spaces of non-compact type. But of course, I will not mention, I don't have I didn't prepare the background for all that. So G ln R acts transitively on the pairs F comma P, where F is a flat and P is a point. F is an arbitrary flat, sorry, maximal flat, and P is a point inside this thing. Okay, so this will prove that all maximal flats have same dimension. And a geodesic, we are considering a geodesic passing through identity. So T going to exponential Tx is contained in a unique maximal flat if and only if X has distinct eigenvalues, so has n eigenvalues. So in our case, distinct eigenvalues. Okay, so this is what we are going to prove. So proof. So you see that we have already proved that G ln R acts by isometries transitively. So given any flat, I can apply some element of G ln R and bring it to identity. I mean, I just fix a point on the flat and apply some isometry and bring it to identity. So that will give me a flat through identity. Okay. So G ln R acts transitively on P and R, and we know that so isometries will take a flat to a flat. So therefore, what I can do is that to prove 1 and 2, I can just concentrate on flats passing through identity. Okay, hence for 1 and 2, so we'll consider flats passing through identity. Okay, so therefore I have to prove that every flat through identity is contained in a maximal flat. But this lemma and then the note, it implies that any flat is the image of image under exponential map of some abelian subalgebra inside S in R, right? So we have seen that. So if suppose F is a flat passing through identity. Suppose F is a flat passing through identity. Okay. So then there is some abelian subalgebra. Then abelian subalgebra, let's say V inside S in R, such that this F is exponential V. So now V has some commuting set of matrices, and all of them are self-adjoint. So therefore, I can simultaneously diagonalize them. Now, simultaneously diagonalize all of this. Diagonalize matrices inside V by some element of let's say S1. Okay. So then we are reduced to so therefore we can assume that V is already contained inside the diagonal. So this implies we can assume that V consists of diagonal matrices only, because when you conjugate, so you'll get some different flat, but I mean different abelian subalgebra, but again that will give you some flat that is passing through identity, because S1 fixes the identity. We can assume that V consists of diagonal matrices. And now, since we are reduced to this, we know that diagonal matrices, this is an abelian subalgebra, and this, the image of that is a flat under exponential map. So therefore, we have proved that any flat can be brought to this standard, this flat. That is the image of this diagonal matrices. Okay. So therefore, the diagonal matrices give you a maximal flat. So every flat has, for instance, same dimension. And this proves not 1 and 2, so 1, it proves 1. This proves 1. So every flat, therefore, so this proves that, hence, the image under exponential map of the diagonal matrices is a maximal flat. Maximal flat, and maybe let us call this F naught. Okay, and so given any flat, F, let's say, there exists some element G inside G in R, such that G acting on F, this is contained inside F naught. This is what we have shown. And so therefore this proves 1. Okay. And so therefore G is acting transitively on the maximal flats. But we have to prove that G acts transitively on the pairs. So for that, it is enough to show that I just choose any point, right, F naught, and I'll show that this on the pairs F naught comma P, it is acting transitively. So to complete the proof of It is enough to show that GL in R acts transitively on the pairs if not comma P. Okay. So this is what you have to show finally. So now how do I show this? So therefore I can show that given any such thing, there is an element of G which will fix if not set wise and take the identity element to that point. So let us say P is exponential x. Okay. So if is the image of this standard diagonal matrix, right? So X is a diagonal matrix. Now we try to find some element of G. So what will work for me? So let's say let G be equal to, so I draw a picture. So this is identity and this is P. So what I'll do is that I will take this midpoint. So then the geodesic inversion about this point, this will just reverse this geodesic. Okay. So what will work perhaps is that, let's see. So G is equal to maybe, so let us call this point Q. So let Q be exponential x by 2. And then take your G to be the sigma identity compose sigma Q. Okay. And then check that this will take, so this flat to itself, and it will take identity element to P. Okay. So check that G of F naught equal to F naught, and G of identity is P. So this proves this number 2. Okay. And to prove number 3, so what do I do? So a geodesic is contained in a unique maximal flat. So by again you can diagonalize X, and we can assume that X is in the diagonal matrices. So that means I have to prove when I have to see when this this element, this diagonal element, the only yeah. So maximal flats. Therefore, you see that yeah. So number 3. So note that so maximal flats through identity, this correspond to, so we have seen that correspond to abelian subalgebras, so maximal abelian subalgebras. Subalgebras of S and R. Right? So now, therefore, so now to prove 3, so what you do is that we can diagonalize this. We can assume without loss of generality that X is diagonal. For proving number 3, we can assume that it is diagonal, right? So now, so when is this diagonal matrix, or this diagonal matrix, this diagonal algebra, so I mean the algebra of diagonal matrices, this is the only maximal abelian, okay, maximal abelian subalgebra of S in R containing this point X, this element X. So now here is a fact that the fact you can easily prove this. So if X is diagonal, then the centralizer of X, so let's say we are taking inside this SNR, is equal to this full diagonal matrices. So all diagonal matrices. If and only if X has distinct eigenvalues. N distinct eigenvalues in this case. So if X is contained inside some maximal abelian subalgebra, that means the subalgebra is centralizing X. But so if I choose X in the diagonal, then it has once it has this distinct eigenvalues, then the centralizer is the only diagonal matrices. Okay. So X is already contained in the flat. I mean the exponential X is this. Yeah. So this geodesic t going to e to the 2x, that is contained already inside the image of exponential math of this image of this diagonal matrices under the exponential math, that is a maximal flat. And now once it has distinct eigenvalues, and this is the only maximal flat that will contain this geodesic. Okay. So this proves that number 3, that this geodesic is contained inside a unique maximal flat if and only if it has distinct eigenvalues. See, GLNR acts on PNR transitively. So suppose I have any flat, fix a point on the flat. So then there is a GLNR element which will take this point to the identity. So that flat will come to a flat which is passing through identity. See, of course, the elements which fixes the identity, they will definitely. But for instance, you can just take any point on the if not and join to identity. This you have geodesic line. So translation along that line, that will take the flat to itself. I mean this kind of element G, this kind of element G. So that is taking identity to P. No, there are, so this, as I said, so maximal flats through identity, they correspond to subalgebras of SNR. The subalgebras, abelian subalgebras of SNR. So there are many abelian subalgebras inside SNR. So suppose that I have some abelian subalgebra, and then you just apply conjugate by, let's say, SONR. So they, yes. Yes, so SONR if you take like that. But you don't have to. You can apply some other element like this G, so this is not an SONR element. That will still take. Yes, like that. Okay? Does it make sense? So this, on the flat, this acts as a translation. So now, this proves number 3, and now I make a definition. So geodesic ray. So geodesic ray means it's a half infinite geodesic, or a geodesic line is called regular geodesic. Regular geodesic if it is contained inside a unique flat, unique maximal flat. Okay. So more generally, you can define. So suppose I have a point and I have some vector, the tangent vector at that point. So that will determine a geodesic line, right? And so then we call the tangent vector regular if the corresponding line is regular geodesic. Okay. This is called a regular geodesic. So, so I should make some remark about because finally, we want to really concentrate on SLNR mod SLNR. So I'll make some remarks on PNR1. Flats inside PNR1. So notice that. So we have noticed that. So if I recall, so if I have X inside SNR, then T going to exponential Tx, that's a geodesic. Okay. So this implies that if X is in SNR0, that is the trace zero matrices inside SNR, then T going to exponential Tx, this is a geodesic in PNR1 passing through identity. And since any geodesic passing through identities of this form, therefore you see that given any point inside PNR1, I can join it to identity. Okay. So this full geodesic line is contained inside PNR1. Okay. Therefore, I'll write this as a proposition or lemma maybe so. PNR1 is a totally geodesic subspace. Subspace of PNR. This means that given any pair of points inside PNR1, I consider the geodesic line that is passing through this. This full geodesic line is going to be inside this PNR1. That is the meaning of saying totally geodesic. So, proof. So, if I have 2 points P1 and P2 inside PNR1, so we know that SLNR is acting transitively on this one. So let G inside SLNR be such that G times G dot P1 is identity. So then the geodesic passing through geodesic joining this joining identity, so that is GP1 and GP2. This is inside. This is contained inside PNR1 because it is of this form T going to exponential Tx. And so therefore exponential Tx for some particular value of T is inside SLNR, and so therefore the full thing will be inside, right? So therefore, so the geodesic lining line joining GP1 and GP2, that is contained inside this, and therefore the geodesic line joining P1, P2, that is also inside PNR. Hence, geodesic line joining this P1, P2 is contained inside PNR1. Okay. And so we have all the things we have proved for PNR. They will be true for this one also. So I'll just write down them as a proposition, and I'll make a remark on the proof. So for instance, the rank of PNR 1 is required, so dimension of maximal flat. That is the same thing as rank of PNR minus 1. So this was the dimension of the diagonal, right? So n minus 1 therefore. And again SL in R acts transitively on the pairs F comma P, where F is a maximal flat inside PNR1. And P is a point inside this flat. Okay? And similar statement about regular geodesics. T going to exponential Tx is a irregular geodesic that is contained in a unique maximal flat. If and only if the eigenvalues of X are all distinct. X has n minus 1 distinct eigenvalues. I'll just make the remarks. The same proof will work. Only you notice that so the scalars. So what I mean is that you take the diagonal matrices inside. So let us give it a name. So let A0 script A0. This is the diagonal matrices inside SN R. And T0 script T0. This will be the diagonal matrices inside the trace 0 matrices. Then you just notice that this A0 is the direct sum of T0 plus the scalar matrices. And so this is the maximal abelian subalgebra inside this trace 0 thing. So this observation will prove all this. And the same proof will work that we have used. Yeah, so recall, so a geodesic is called regular if it is contained inside a unique maximal flat. Maximal flat. Otherwise, we call it singular. Okay. So next, what I define is what is called a Weyl chamber. So so what is this? So fix a point and a flat. So let F be a flat, maximal flat, and I have a point P inside F. Okay. Then so consider geodesic rays that are starting from P. So all the geodesic rays. So some of them are regular and some of them are not regular, singular. Okay. So then and Weyl chamber. So what you do is that you remove all the singular geodesic rays from this F. So this will be some disconnected set. So a connected component of that is called a Weyl chamber. A Weyl chamber contained inside F with tip P, okay, is a connected component. We'll see an example. So component of the union of the regular geodesic rays. So consider all the regular geodesic rays starting from P. So that will be some open subset of this, but it is not connected. So take one connected component. So that is a Weyl chamber. Okay? Yeah. No. You have a flat. You have a point. Now consider all the geodesic regular geodesics. Okay. The union of that is an open subset of F. Union of the yes all the points that are sitting on some regular geodesics. So, no. So then it's a Weyl chamber. So I'll give an example. So so therefore, what is a Weyl chamber with tip F? So that means it is so there is a flat F, maximal flat F, and so this Weyl chamber is sitting on this flat. Yes. Well, no, I'm sorry. So this is not one. This should be n right there. Thank you. Okay, but the dimension of all this T naught, that is n minus 1. So so let me give an example. So so for instance, you have this A naught. So this is the set of all diagonal matrices x1, x2, xn. Okay, and the image under the exponential map, that will give me a maximal flat. So here I'll take F to be exponential A naught, and I'll take P to be identity exponential of 0. So, and so I want to understand what are the Weyl chambers here. So for that, so notice that so image of something will be on a regular geodesic if and only if the eigenvalues are all distinct. N eigenvalues are distinct. Okay. So here this singular, some geodesic is singular, T going to exponential x, Tx is so x is of this form, okay, is singular. So if and only if xi, small xi equal to small xj for some I not equal to j. So where I am assuming that x is this matrix x1, x2, xn. So these are my singular geodesics, right? So therefore, what are all the singular things? So therefore, so let maybe I call it something. So let fi, maybe fij. This is a subset. Maybe I should call it something else. Anyway, so fij. So this is a bad notation. Sorry. So this is the set of all matrices x1, x2, xn, where xi equal to xj. Okay. So this is an n-dimensional vector space, and this is a hyperplane inside that. Okay. So so we define it for I not equal to j. So then this singular geodesics correspond to this the union of the singular geodesic. So that is simply the union of all this exponential fij, where I is not equal to j. Okay. So in this vector space, individual vector space, we have some hyperplanes. So there are n choose 2 hyperplanes. You throw them, so you have some connected component, and take the exponential map. So the image of those things, they correspond to the Weyl chambers. Okay? Does it make sense? So let us say for n equal to 3. So for n equal to 3, so therefore I have only x1, x2, x3. So therefore the Weyl chambers in this example, this correspond to this correspond to the open sets. So I have x1, x2, x3, and correspond to the open subsets of this x1, this space of diagonal matrices. So the open subsets of the form. So you can check that. Yeah. Maybe I call it W sigma, where W sigma is matrices. It is true in this generality also. So x1, x2, just 3. So x1, x2, x3 says that x sigma 1 is bigger than x sigma 2 is bigger than x sigma 3. So I'll just leave this for you to check. So there, this sigma is varying over the permutations on the letters 1, 2, 3. So where sigma is in S3, the permutation group on 3 letters. So there are therefore 6 Weyl chambers. So in general, you will have sigma x sigma 1 bigger than x sigma 2 and so on till x sigma 1, like that. So that will correspond to the Weyl chambers. Okay, and so that's that. And similarly, so Weyl chambers in PNR1 so again, so yeah, so maximal flats, we have seen that this correspond to maximal abelian subalgebras of SON R0. And so for example here, so if I take, so if F0 here is the exponential of T0, okay, then again, so again, so here the Weyl chambers correspond to the same. This matrices x1, x2, xn, such that x sigma 1 bigger than x sigma 2 and so on. Like this. But only difference is that here the trace is 0. But still, you'll have the same number of Weyl chambers. Okay. So here is something for you to check is that so note that so inside this in R1, suppose I have this flat, these Weyl chambers, and then you see that SN, the permutation matrix is sitting inside the GL in R. And so since it is every such matrix is in ON, so that will fix the identity. And you can check that this that will permute these Weyl chambers. So permutation matrices in GL and R permutes the Weyl chambers. In F0. So this proves that GL and R acts transitively on the Weyl chambers. So this is something that will be useful later. Yeah, so most of the thing I am just leaving small exercises, so because I don't have enough time to prove all this. Yes. No. So Weyl chambers you have seen they are disjoint sets. What is that? So that is a connected component. Yes. Yes, it is a connected thing. So so for S3, so it has I mean the P31, let's say. So therefore this is matrices of this form with trace 0, so that is dimension 2. So the flats have dimension 2, so Euclidean plane. And then so yeah, I have not drawn this picture, so because I didn't want to explain. Yeah. No, I said this corresponds to this thing inside S and R, so that's what I am saying. The trace is 0, and so therefore to find the Weyl chamber, so you remove some lines from this plane, right? And the lines you can draw like this. So I purposely omitted that. So in this case, this P3R so then they look like this. So there is a reason. So these are the Weyl chambers, and these are the singular lines. So there is a reason for us to draw like this, because we know precisely the angle. So S and R, right, as an inner product. So we know the angles between these lines. So that's why we draw like this. So inside the T0, so it will look like this picture. So that is for this E3R. And yeah. Yes, those lines are the singular. Okay, and those shaded things are the Weyl chambers. No, base point is not contained in. No, I am not included. So now I want to move to a new topic. So boundary at infinity. So there is a natural compactification of this kind of space, the symmetric spaces with a non-positive curvature. And so now I think I just concentrate on, so for us I'll just say G is SLN R, and A, manifold M is PNR1. I'll just concentrate on this. So there is a way to compactify this M. So what we do is the following. So definition. So partial M is the boundary. So this is the equivalence classes of asymptotic geodesics. Geodesic rays. That is, what you do is that, suppose you have two geodesic rays. Suppose gamma 1, gamma 2 inside M are two geodesic rays. So I really mean here the image. So geodesic rays. So we say that they are asymptotic. So gamma 1, gamma 2 are asymptotic if the housed of distance of this gamma 1 and gamma 2 that is finite. Okay. So for instance, in the case of a hyperbolic plane, we have seen that so this kind of thing, so they cannot be very precise. So, so asymptotic geodesics we draw like this. And for the plane, suppose I take the axis and y axis, they are clearly not asymptotic. Their house of distance is not finite. So we consider all the geodesic rays which are asymptotic. So this will define an equivalence relation on the set of geodesic rays. So we say gamma 1 equivalent to gamma 2 if their house of distance is finite. And the set of all equivalence classes I'll denote by past M. Okay? And this is called the visual boundary of this. So all this that I'm going to do now, so this can be defined for general cat 0 spaces, but I have not defined at all. So I'll just omit that. And one can define a nice topology on this. So cone topology. What is cone topology? So I have to just tell you the neighborhoods of a point. So what I do is that, so I'll purposely draw like this. So suppose I have some fix a point. So yeah, maybe I should say just before that I just use a fact. Suppose gamma inside M is a geodesic ray. And I have a point P inside M, then there is a unique geodesic ray which is asymptotic to gamma and passing through P. So then there is a unique geodesic ray in M starting from P and asymptotic to gamma. Starting from P and asymptotic to gamma. So therefore, if I just fix a point and consider all the geodesic rays that are coming out of this point, so they will give me all the classes, all the asymptotic classes. So now to define this cone topology, I'll fix a point. So fix a point P, maybe P naught at M. Okay. So so every asymptotic class is given by some geodesic ray that is starting from one unique geodesic ray starting from here. So let gamma be a geodesic ray starting from P naught. Okay. So then the cone topology. So I had to define the neighborhood of this one, and the neighborhoods are defined like this. So so for all R positive and epsilon positive, we define, I'll just draw a picture, I'll not write down the neighborhood. Gamma R epsilon, we define like this. I'll just draw a picture. So you do the following. So you have this is gamma and this is P naught. Okay. So then you consider the radius R ball about P naught. So that will be something like this. Okay. And so this is the radius R ball. So now you consider all the geodesic lines. So this is my gamma, geodesic rays, and see where this is hitting. So let us say this is alpha. So you consider alpha R, and this is your gamma R. So then you consider the set of all alpha such that the distance of alpha R and gamma R that is smaller than epsilon. Okay. So this is the set of all alpha such that alpha 0 is P, and distance between alpha r and gamma r is less than epsilon. So this is giving you the neighborhoods of this point gamma. And one can show that this does not depend on, this topology does not depend on the point you have chosen. Not. And in our case, so what happens is that, so if I just take any sphere about, so take r radius sphere, any r radius sphere, about P naught, and then therefore for every point on the sphere, I have a unique geodesic ray that is connecting P naught to this, and right. So that will give me a homeomorphism from this sphere to this this partial M. So in our case, in this case, this is homeomorphic to the n sphere, to the sphere of dimension. So here in the space, the dimension of this one is the dimension of PNR, PNR1. So in this case, M minus 1. So this space is a sphere. So I have several comments. So I will not write down. I'll just say what I wanted to say. So first of all, important thing is that it will not depend on the base point P naught. And then if I have any isometry of the M, that will induce, so because isometry will take geodesic to geodesic, so it will induce a map from the partial M to partial M, and one can prove that it's a homeomorphism. And so therefore, the group G is acting naturally by homeomorphism on this partial M. So that will be very important for us later. And so one more comment is that in the hyperbolic situation, you have seen that given any point at infinity, any 2 points, we can join them by some geodesic. So in this case, it will not be true. So if I have 2 points, there may be no geodesic line such that it is asymptotic to both the geodesic rays. It is not true. For example, because this this will contain, so in this bigger than n bigger than equal to 3, so this will contain flats. The flats are isometrically embedded subspaces here. So therefore you can see easily, so if I take the x-axis and y-axis in the plane, so these kind of things are here. So it cannot be joined by some geodesic line. I mean, this is not a proof. So. But at least in the plane, you cannot join them by geodesic. So therefore, given any pair of points, there may be no geodesic line which is converging to this point at infinity. So this is quite a difference from this from the hyperbolic geometry. So one important thing that I need, I just state to define the rest of the things. So here, so I don't have time, so I just state most of the things and not prove. So R infinity, so let us say we have fixed this, R infinity will correspond to the equivalence classes of geodesic rays gamma, such that gamma is a regular geodesic. Regular geodesic. So R, this is a subset of the partial M, and the fact is that it's clear that G stabilizes this, stabilizes R infinity. So if I take any regular geodesic ray and I hit by some isometry, then again it will be some regular geodesic. So this is a G stable subset of this partial M. Okay. And so then next I wanted to define what is called the Furstenberg boundary of this symmetric spaces. So I'll denote this by if M infinity. So what is this? So instead of considering the geodesic rays and their asymptotic classes, So now you consider asymptotic classes of Weyl chambers. Okay, so this is, as I said, it is simply the asymptotic classes of Weyl chambers. Okay, so now notice that any regular geodesic ray determines a unique Weyl chamber. Right? Because so suppose I have a geodesic ray starting from a point P, then this geodesic ray is contained in a unique maximal flat F. And then for this point P, I'll consider all the Weyl chambers. So this is sitting inside one of the connected components, right? So it is contained inside a unique Weyl chamber. So every geodesic ray or regular, that will determine a unique Weyl chamber. So therefore, there is a map from R infinity to Fm infinity. And so we'll use that to define a topology on Fm infinity. Okay? So this gives a map from R infinity to Fm infinity. So notice that, so GLN, so in our case G, so I shouldn't say, so G acts on Fm infinity. So if I have a Weyl chamber and I hit by some isometry, then again it's a Weyl chamber. And this, so this map is G equivariant. And we define a topology on Fm infinity, the quotient topology, using this map. So, therefore, I have this space Fm infinity, and this is called the Furstenberg boundary of this. And for this, so I wanted to give an example. So, and now we want to do some example. So, yeah, so, so I'll state some facts, and maybe if I have time, I'll just do one example. So, so fact is that, so GLN, G here acts on this. Fact is that this action is transitive. G action on Fm infinity is transitive. And another interesting fact, just like that reminds you of the hyperbolic geometry, given a pair of points here, given a pair of Weyl chambers, W1 and W2, there is a flat F, maximal flat F, which is asymptotic to both W1 and W2. Just like in the hyperbolic geometry, if I have pair of points, I can connect them by the geodesic. So geodesic are the maximal flats there. So here, if I have two Weyl chambers, I can connect them. Okay? So I just wanted to do this example. But yeah, so just quickly, I just mentioned this, that suppose in this case, I take some point xi inside this, so we are trying to understand this Fm infinity from this. And so this, so this corresponds to some geodesic ray passing through identity, so a unique geodesic ray. So this gives me a geodesic t going to exponential tx. Okay, and so now let lambda 1, lambda 2, lambda k with the distinct eigenvalues in decreasing order. The eigenvalues, all the eigenvalues of X, and let EI with eigenspace, corresponding eigenspaces. So then what you do is that you define this Vi to be simply the direct sum of Vj, j is less than or equal to I. So then this gives me what is called a flag inside the Rn. This V1 contained inside V2 and so Pk, this will be Rn. This is a flag. So for every point I have a set of eigenvalues and I have some flag like this. So this is called, let us just write it, I don't know how to write it, so maybe just write it as this vector, something like that. And this as some flag script f. So this pair determines xi completely. So that means given a point I have a unique one, and for every something like this and a flag I'll get a point. So this gives me a one-on correspondence between the eigenvalue flag pair to the points, okay? And then the Weyl chambers will correspond to simply forget the data about the eigenvalues, correspond to the flags. And then one can prove that this Fm infinity is homeomorphic to the space of flags in this case. And since I'll just say it, so I don't have time, so G action on Fm infinity is transitive, so therefore this can be understood as G modulo the stabilizer of one flag. So for instance, if I take this standard Weyl chamber that I had drawn some times back, so I take the abelian diagonal things x1, x2, xn, and take x1 bigger than x2 and so on till xn. That will determine a Weyl chamber. And take this stabilizer of that, so then you will see it is simply the set of all, the subgroup of all upper triangular matrices. Therefore, in this case, in our case, this will be G modulo the upper triangular matrices. And so in particular, this is compact and so on. I'll stop.